elaborate and quite difficult to read. Nobody reads this, so it immediately gets optimized. And you see that it shrinks in size. It becomes smaller, but still we have some redundancy here and some unnecessary stuff like the initial microcode had all flags, processor flags, everything. In fact, let's take the overflow flag, OF. I don't think that it's used anywhere in the program. It's used very rarely. But we do generate it anyway, because just to be precise. But we cannot remove it right now because we cannot prove it at the basic block level. Maybe another basic block use it. So what happens is that we optimize it further. We optimize first local optimization. And local optimization, this step will start already to lump instructions into big expressions. See the second instruction. You see that we have already LDX, which means load from memory. And as a memory address, we have ECX plus 4 already. So we have microcode instructions maybe nested into each other. And this way, we will get nice expressions at the end. We still have processor condition codes here, OF, CF, ZF, SF. I think that all of them will go because we already have G jump 0 at the end, and nobody else will use these condition codes. And this is the task of the global optimization step. You see, after the global optimization step, is very small now. The LDX register, the LDX instruction got propagated into the jump instruction. So we have very nice thing here. By the way, no, we cannot do it. We cannot do it here. Anyway, if you noticed, we started with something reasonable, like 5 instructions, 7 instructions. We made it bloat into 106,000, I don't know how many, bigger, and after we optimized it back into something smaller. So that's how it works. It becomes first very big, and after it shrinks size, and we get nice result at the end, very small. After that, we replace all registers and stack addresses by local variables. This is something I had to devise a special algorithm for that. And after that, we will go and perform structural analysis. What we do here, the structural analysis, it takes the control graph. You see that it's the control graph is very similar to the original graph view in IDA. And we have the control graph. And looking at the control graph as a human being, I can tell, okay, block number 1, it passes execution either to block number 2 or block number 3, depending on some condition. So it looks like if not a condition, then we execute number 2. Otherwise, we don't do anything. So it's the if condition, the if block. If you look at the block number 6, it looks like a loop. We go back. So we repeat until the condition is satisfied. The structural analysis extracts this information from the graph and represents it as a tree, like this. And you see that we have if, then else, do, while, and all this information. It's encoded in this tree now. And this algorithm is quite robust, and I use, again, something special, not seen in other decompilers, special structural analysis algorithm. It's very robust. It can handle any graph. I even run it on random graphs. I was generating random graph and running this algorithm. So even if you have a really bad graph with many edges, it will generate all necessary go-tos. So you will still have an output. Maybe the output will be really difficult to read because you have too many edges, or in other words, too many go-tos, but it still will be possible. After that, we generate pseudocode based on this tree, and based on our pseudocode, we can say, for example, block number 12 here on the lower right corner, it's a block. A block means that we have just a linear execution. So we have to generate code for the block number 10 and after for the block number 11. I think that this block corresponds to the last 3 instructions, to the last 3 lines. We call a subroutine, we copy the result, and we return. The output is correct because we generate all casts but there are too many casts. In fact, it's almost unreadable. Again, this is not visible to anyone. The decompiler immediately applies transformation rules to that, and it generates something like that. This is almost readable. This is something that the decompiler can give you, but after that you have to improve it. As the same way as with IDA. When you just take a listing, you should not take it as for given, you must improve it. Here we have some casts, for example, this plus 4, and we have a cast here for the double word, a pointer, and we dereference it. We take a value at that address. Why so complex? Why so awkward? The reason is that the decompiler does not know that this is a pointer. It thinks that it's just a normal integer, and by the rules of the C language, you cannot dereference an integer. That's why it puts a double word like this. A good type analysis, very good type analysis could deduce, looking at the code, say, okay, we have this plus 4, apparently at this plus 4 we have a pointer. Unfortunately, the type recovery algorithm that we use in right now, it's not very good, not good enough. It will be improved in the future, but for the moment you have to do it yourself. For example, we have to tell that this, I think that it's a pointer to a structure. Usually it's a pointer to a structure. V1 is a copy of this, so it must be the same thing. The same way as in IDA, you go and say, I want to change the type of this or that, or V1 or anything. And you can change things. You can, by just saying that this is a pointer, the output, you can modify the output this way. You can add comments, you can rename variables, functions, you can do everything you want. Please note that the initial assembly was too long to be displayed on one slide, so that's why I did not even display it. But the final result is quite simple. I think that it's better now to switch to some demos and show you how it works, because a live demo is always better than slides. Okay, we have a function here. It takes one argument, as we see, and after we take, we put this argument, we take plus 8, we put it in the edx plus 4, all that stuff. You see that you have to analyze this. Okay, I'm lazy, I just ask the decompiler to generate an output for me. I press tab, and that's what I have. In general, decompilation is very fast. It's almost instantaneous, so unless in some cases it can take really huge time. If you have a function, let's say 200 kilobytes of code, then it will take time. Yeah, it may take even an hour or even more longer. Well, that's how it works. But I'm not satisfied with the output. You see that we have A1 plus 4 plus 8, all that stuff. It's not good. Again, why it happened? Because the decompiler does not know that A1 is a pointer. Okay, I will tell it. I will right click and say, please create, there are many ways of doing it. I can say, I want to set the type manually, I can convert it, I can convert to a structure pointer. In this case, I am really lazy, I will just ask, please create a new structure type for me, like this. This is what is proposed by the decompiler. It looked at the code and found that there are references like this. I just accept it. Still not that good. I think that I better go another way. In fact, I have already, I will show you. I have, in fact, the argument that we are having, it's a pointer to a graph that has some nodes, as you see here, and and each node has an array of successors and predecessors, and it has also some attributes, and each attribute has an ID, has a name, a type, value. So you see, it's quite standard stuff. What I will do, I will explain all this to the decompiler. It's very easy to do. First of all, I will tell IDA, ask IDA to parse the file that I have, parse the C header file. This is not something that comes from the decompiler. This is something that basic functionality that exists in IDA since a long time. The compilation is successful. So I have all my types ready. And now I say that A1, I know the type. It's not a pointer to struct A1. It's a pointer to graph underscore T. So it's a pointer. I put star. And I press OK. And that's okay. I think that this is the best you can have. I can, of course, I can rename this. I can call graph like this. So I have, is it visible enough? Let me make the font bigger. I think that the font is too small. Is it better like this? So instead of this code, you have to decipher anyway. You have only this code. Yes, you have to explain things first. You have to explain the types. But as soon as you do, you have very nice code. Another sample. What is this? Okay, we have a function that takes some arguments and calls string compare many times. Makes some comparisons, you see. Jump 0 many times. And after it calls print. And that's it. Okay, instead of looking at this code, I just press tab. And that's what I have. In fact, the whole function is one if statement. If this, or that, or this, and so on. The result is 0. Otherwise, the result is 1. Apparently, here we just check we perform some checks, and we do this or that. By the way, I can now replace things. I can say, this is, I know that it is, let's say, okay. I will just rename it okay. And after I will say that this 0 is false, and this is true, and these numbers, okay, I don't like them. I change them, for example, into hexadecimal. No, hexadecimal is not good. I will change it to characters. Characters look nice. You see, you do the same things as with IDA. And without doing these things, the output looks ugly. And I think that this is, I will call it magic. And I can add a comment saying failed. See that the comments are here. So the compiler is interactive, fully interactive, as you might suspect. Another sample, another example, what we do here, we create something. Okay, I will press, here we have a loop, we have to do this, something. Anyway, I will just press tab. Okay. Again, have a nice function, and you see that the compiler could recognize the for statement, the for loop. Apparently here we take, okay, what do we do here? We take a malloc, we allocate some size, okay, we take some memory, and after we initialize this with some values starting 0, 1, 2, 3, 4, and up to size. And the second, what we do here, we swap them. Okay. So looking at this code is much easier to read than this code. It's out of question that you can read. This code is also readable, but you spend much more time. You have to say, okay, this push, what is this? Okay, we just save a register. The decompiler hides all this information and just shows you nice result. Okay, do I have anything else to show? Okay, here we have a sequence of calls. I see that we call init sub many times. Okay, just press it. Yeah, I like this better. So we have a nice, almost a table. So we initialize files, segments, functions, registers, and so on. Easy to read again. What else here? Main. No. For me, at least, maybe because I spent so much time with C code, you spent a lot of time with assembly code. So maybe that's why you would prefer this especially if you never programmed in C. But if you program in C, you see that the difference is just very big.